Okay, hello everyone. Assalamualaikum warahmatullahi wabarakatuh. Um, Today we'll be discussing another concept in discrete mathematics that will be a very important concept in programming. The concept is recursion. Okay, today we'll define what is recursion in discrete mathematics, and basically we'll use this concept in algorithm. So in algorithm and programming context, or in computer science context, we will use as an algorithm. So we call it a recursive algorithm. And then after that, we'll have a look what is the difference between a recursive and uh, the basic iteration. Okay, now what is recursion? Okay, so basically recursion inspired by the nature. So you can have a look, for example, here there is replication, right? There is replication. So basically here we can find uh, the same shapes, but we have the smaller one. Okay, so that's it, a recursion in the nature. Okay, another one, we can have a look this one. So the same thing, we have repetition as well here. We have the big one and we have the smaller one, which is basically the same shape. Okay, so that is the definition of recursion in nature. Okay, now what is a recursive in maths or in computer science? Okay, so to give you an example, for example, we have a sequence of number. So to define sequence of number, we have two ways. The first way is by using explicit formula that I thought you have been familiar in your senior high school. So for example, we have sequence of number 0, 1, 2, 3, and so on. Usually we can define by using explicit formula. Okay, so for example, here we have a 0, 1, 2, and then a var, 8, and so on. So we can define using explicit formula like this. So we have an equal to 2 power n. So for example, if I want to know what is the a var, for example, like this, a var, uh, the fourth element. So what is the fourth element? So just put into the formula. So we have 2 power. Sorry, I can find power. So just like this. So we have 2 power n. So we have n is 4, right? So we have 2 power 4. So basically this one is 2 times 2 times 2, sorry, times 2 and times 2. This is basically 16, right? And so on. Okay, that's what we call explicit formula. But we have different way how to define that sequence of number by using our recursive form. Okay, so by using recursive form, we have division like this. So we define the a0 equal to 1, or in other we can say like this: if n equal to 0, then it will be equal to 1. Yeah, we check if n equal to 0, so it will be equal to 1. Otherwise, we define like this. Then if it's not if n is not equal to 0, then it's defined as an plus 1 equal to 2 times an. An plus 1 is equal to 2 times an. Okay. Okay. In which n equal to 0, 1, 2, and so on. Okay. Okay, and the same like before, we have an here equal to 0, 1, 2, 3, and so sorry, I have made mistake before, and here is 0, 1, 2, 3, and so on. So it's integer starting from 0. Okay, the same like here. So n equal to 0, 1, 2, and so on, which is basically whole numbers starting from 0. Okay, all right. So let's have a look here. So by using the same thing here, let's say I have, so by using the second definition here, I can define, for example, a var equal to, for example, here, is it n a var, so we have n equal to var, right? N is var, okay? So we put into the definition of recursive form, we can check, is it n equal to 0? No, right? So we have here, so basically by using the second definition, so a var will be equal to 2, yeah, 2 times 2 times an. So we have n plus 1 is 4, because an plus 1 is 4, so we have an equal to 3, right? So we have a 3. Okay, all right. Now we have 2 times a3. What is a3? So put into the recursive definition again. Is n equal to 0? No, right? Because we have n equal to 3. So we have the definition again. So we have just put the previous one, 2 times. Now we have a3. So from this definition, we have a3 as 2 times a2, right? 2 times a2. Okay. And then let me copy again. Okay. Now let's find what is a2. Okay, a2 just put into the definition, is n equal to 0? No, because we have n2, right? Okay, so we have sorry, so we must change a2 now. A2 as 2 times a1, right? 2 times a1, which is basically equal to a1. Okay, all right. Now let's find a1. What is a1 here? Okay, sorry. Okay, so what is a1? A1, okay. So we have a1 here. Now let's check it. It's a1, a0 equal to, sorry, is it n equal to 0? No, right? So because it's not equal to 0, so we can find the definition. But this one, an plus 1 is 2 times an. Okay, so we have n plus 1 equal to 1. So n is 0, right? Because n plus 1 is 1, so n is 0. So we have this one, a1 equal to a minus 1, 2 times 2 times a0, right? A0. Okay, and then let's find what is the value of a0. Just put into the definition, is n equal to 0? Yes, right? So we can replace a0 with 1. Okay. Okay, let me put like this. So we can have this one. Okay, equal to 1. Because when n equal to 0, the value is 1. So we have this one. So we can find out here 2 times 2. We have 4, right? 4 times 2 is 8. 8 times 2 is 16. 16 times 1, which basically is equal to 16. Okay, so we have the same value, right? By using explicit formula and using a recursive form, uh, uh, the result is the same. Okay, all right. So let's have a look on on another example. Okay, for example, I have function f. Let's say I have function f that is defined recursively by like this. If n equal to 0, then the value is 3. Okay. Otherwise, if n not equal to 0, then we define like this. Fn plus 1 equal to 2 times Fn plus 3. Okay, so what is the value of F1, F2, F3, and F4? So we can find like this. F1. Okay, so we have n is 1, right? So we put here, is n equal to 0? No, because n is 1, right? Okay, so we define with the second definition. So we have Fn plus 1 equal to 2 times Fn plus 3. So because we have n plus 1 is 1, so Fn will be 0, right? So we'll have 2 times, just use this definition, 2 times Fn. Because n plus 1 is 1, so we have Fn is F0, right? Okay, so we have 2 times F0 using this definition plus 3, plus 3, okay? And because let's find f0. F0 it's mean the n is 0. So if we put in this definition, is n equal to 0? Yes, right? So just put f now f0 with 3. So we found it 2 times 3. Yeah, replace f null with 3. So we have 2 times 3. It is 6. 6 plus 3, which is equal to 9. Okay, so f1 equal to 9. Okay, all right. Now what about f2? F2, so n is 2, so it's not equal to 0, so we use the second definition. Fn plus 1 equal to 2 Fn plus 3. So because n plus 1 is 2, then n is 1. So we have this definition, 2 times F1 plus 3. And we know that from previous definition, F1 is a 9, right? So just replace F1 with 9. So we have 2 times 9, which is 18. And then 18 plus 3, we have 21. Okay. And the same thing for F3 and F4. So for example here, F3 we find using this definition, right? So we have 2 times F2 plus 3. From the previous definition, we have F2 equal to 21. So we have 2 times 21. So we have 42. And then 42 plus 3. So we have 45. And the same thing for V4. So we have 2 times F4, yeah. So F4 equal to 2 times F3 plus 3. And then we know from the previous definition, F3 is equal to 45. So we have 2 times 45, which is 90. And then 90 plus 3. So we got 93. Okay. Okay, let's have a look to another example. Okay. You know vectorial, right? Vectorial. Just to remind you, for example, if I have 3 factorial, for example, so basically it will be equal to 3 times 2 times 1. Okay, which is equal to 6. Okay, that's the definition that you have you have familiar with. Okay, but we can define factorial in different way by using our recursive definition like this. Okay, so we have the initial value. If n equal to 0, then the value, then it will return 1, or the value will be 1. Otherwise, if n is not equal to 0, then we define like this: fn equal to n or fn, which is basically n factorial. Yeah, because we define this is fn equal to n factorial. So basically we have fn equal to n vectorial equal to n times n minus 1 factorial. Okay, or in other way, we have this one n times f n minus 1. Okay, so what about if f5 uh, n change with 5? So because 5 is not equal to 0, so we use the second definition. So basic, we got 5 by using this one, right? N times n minus 1 factorial. So we have 5 times ever, ever, and we have an ever basically is 5 times we define f4 as n times n minus 1 factorial. So we got 4 times f3. Okay, and then f3 we got 3 times f3. Okay, just back to this definition. Okay, and then we got f2, so f2 will be uh, sorry, f2 will be equal to 2 times f1. Okay, 2 times f1, and by using the same definition we got f1 as 1 times f0, right? Okay, and because f0 equal to 1, so just replace f0 with 1. So we got this one: 4 times 4 times 5 times 4 times 3 times 2 times 1 times 1. Okay, so we got 120. Okay, you can use like this cross or dot. Basically, it's the same thing. So you can use like this one. It's basically the same. Okay. All right. Now let's have a look on another example. Okay. Now we have sequence of Fibonacci number. Okay. Okay. So we can define the Fibonacci number like this. So if n, let's say fn, right? So we have fn. If n equal to 0, it will be 0, and if n equal to 1 or f1, it will be equal to 1. Otherwise, if n is not equal to 0 or n is not equal to 1, then we have fn equal to fn minus 1 plus fn minus 2 for n equal to 2, 3, 4, and so on. So by using this definition, we can find what is ever. Okay, so ever n equal to 4, right? Because n equal to 4, so n is not equal to 0 and n is not equal to 1. So use this definition. So we can define ever as f2 plus f3 plus f2. We have n4 and we have n minus 1, f3, and n minus 2 is f2. Okay. All right. And then what is f3? Put to the definition because we have n3, right? N equal to 3 and n is not equal to 0 or n is equal to 1. So we use the third definition. So we have fn equal to fn minus 1 plus fn minus 2. So we have f2 equal to f2 plus f1. Okay, and we have f2 as f1 plus f0. Okay, why? Because from this definition, fn equal to fn minus 1 plus fn minus 2. So because n is 2, so we have 2 minus 1, which is equal to 1, and n minus 2. So it's meant 2 minus 2. So we have f0. Okay. Okay, so we have this one. All right. Okay, now let's have a look on this one. We have f2, f1 plus f0, right? So you know this one, if f1 equal to 1 and f0 equal to 0. So we have this one, f2 plus f1, 1, yeah. So 0 plus 1 equal to 1. And then plus f1 again, it's mean 1 plus 1. So we have 2. And then 2 plus f0. F0 is 0, so 2 plus 0 is basically 2. So we have f2 plus f2 plus 2. Okay, and then what is f2? Back to the definition. F2 is f1 plus f0. Okay, f2 is f1 plus f0 from this definition. Okay. And we know that f1 is 1 and f0 is 0, right? So we have 1 plus 0. Is it 1? And 1 plus 2. So we got 3. Okay, so f var is 3. And so on. You can carry on using f5 with using the same definition. Okay, so from the example, we can make a generalization. So the recursive definition, we have two parts. The first part is the basis step. The basic step, for example, like this one. So we have the basic step is this one, f0 and f1. Or in this case, we have the base case is f0. Yeah, f0 equal to 1. That's what we call the base case or basis step. And then the second part is recursive step. Our recursive step is we define the thing with the thing itself. Yeah. So for example, here we have fn, right? Fn equal to n times n minus 1. We have fn, right? So we define n with n here. Okay. Okay, that's what we call recursive step. Or in this one, we define this one is the recursive step. So we define fn with f with f as well. Yeah, we define f with f. The difference is on the value of n. So if here is n, then on the right side is n minus 1 and n minus 2. But basically it's still the same f. Okay. All right. Okay, so that's the technical definition of recursion. So we have the first step, what we call the base case or basis step, and then we have the second part is recursive step. Okay, another example. Okay, now let's say we want to define a set of positive integer. Okay, the set of positive integer. So we can define the basis step as 1 is member of set S. 1 is member of set S, which is set of positive integer. Okay, 1 member of S of set S. Then the recursive step is like this. If X is member of S, then X plus 1 is member of S as well. So we have 1 already, right? So because 1 is member of S, then X plus 1 will be the member of S as well. So we already have 1. So 1 is member of the set S. Then n plus 1 or 1 plus 1 will be the member of S as well. So we have 1 is member of S. Because 1 is member of S, then we have 2 member of S. because 2 is member of S, then 3 is member of S as well, and so on. So basically any number greater than 0 is member of positive integer. Okay, another example, we have set of odd positive integer. So we can define the basis step is 1 is member of set S. So big, and then the recursive step, if X is member of S, then X plus 2 is member of S as well. So because 1 is member of S, so 1 plus 2 is the member of S as well. So we have 3. 1 is member of S, then 3 is member of S, and then 3 plus 2, which is 5, is also member of S. 5 member of S, then 7 is member of S, and so on. So any odd number uh, greater than starting from 1 and then adds by 2. So it will be set of positive, odd positive integer. Okay, using the same way, we can define set of positive integer power of 3 as like this. The base step is 3 member of S, and then if X is member of S, then 3 times X is member of S. So we got 3, and then we got 3 times 3, is 9, and then 9 times 3, 27, and so on. Okay, that's uh, the recursive definition of set. Okay. Okay, now in the context of computer science, function usually will be a method in programming, or basically in general way, we call it an algorithm. So function will become a method, or generally we call it algorithm. Okay, so you will use this recursive uh, recursive definition when you come into programming. We call it recursive algorithm, or more technically, we call it recursive method. So you will create recursive method in coding or in programming. You'll find it next semester in algorithm and programming class. Okay, yeah, let's define a great common divisor. Great common divisor. Okay, we can define great common divisor like this. So we have the basis step like this. So we define the GCD like this, a GCD of A comma B. So we have GCD A comma B. We have the requirement here. A must be less than B. So in other way, B must be greater than A. Okay, and then A must be greater than 0. So at least A equal to 1. Okay, so we have the basis step. On the basis step, GCD of 0 comma B is equal to B. So if A is 0, then the value is B. Otherwise, if uh, A is not equal to 0, then we define GCD A comma B as GCD of B modulus A comma A. Okay, B modulus A comma A. Please remember what is the definition of mod. Okay, so for example, what is the GCD of 5 comma 8? Okay, so let's have a look here. Is it A equal to 0? No, right? So because we have 5, so it's not equal to 0. So we use the second definition. So we have GCD of A comma B equal to GCD of B modulus A comma A. So we have A5 and B is 8. So we got this one. GCD equal to GCD B is 8, right? 8 modulus A. Modulus A is 5, comma 5. So 8 modulus 5. Yeah. 8 modulus 5. What is the remainder when it's divided by 5? What is the remainder when it is divided by 5? So it's divided 5, we got 1, right? And the remainder is 3. So uh, we found this one, 8 modulus 5 as 3 here. So we got as GCD 3 comma 5. Okay, so let's have a look again here. What is the GCD of 3 comma 5? So just check whether a equal to 0, because we got a 3, a equal to 3, so a is not 0, so we use the second definition here. Okay, and then again, so we got GCD of 5 modulus 3 comma 3. 5 modulus 3. Okay, what is the remainder when 5 is divided by 3? So 5 divided by 3, so we got 1, and the remainder is 2, right? So we got 2 here. So we got GCD of 2 comma 3. So we got GCD of 2 comma 3, and because we got a is not 0, so in the same way we got GCD of 3 modulus 2 comma 2. Okay, and because 3 modulus 3 is 1, right? 2 is divided by 2, we got 1, and the remainder is 1, so we got GCD 1 comma 2. Okay, what is the GCD of 1 comma 2? We check it. A is 1, right? So a is not equal to 0, so we use the second definition, this one. Okay, so in the same way, we got this one. GCD of 1 comma 2 is GCD 2 modulus 1. Okay, 2 modulus 1. 2 is divided by 1, right? We got 2, right? 2 divided by 1 is 2, and the remainder is 0. So we got 0 here. So we got GCD of 2 comma 1. Okay, and because uh, the GCD of 0 comma 1, and which is a is 0, right? So because a is 0, so it is equal to 1. So finally we got that the GCD of 5 comma 8 is 1. Okay, all right. So now let's have a look on another example. For example, I have GCD of, okay, let's say I have A must be less than B, right? So for example, I want to have a look 2 and 6, let's say 2 and 6. Okay, 2 and 6, what is the GCD of 2 and 6? Okay, so let's check it. Is A equal to 0? No, right? So because it's not equal to 0, so basically GCD of 2 comma 6 is, it will be equal to this one, B modulus A. So we got 6 modulus 2 comma A. We got A is 2, right? Okay, all right. So what is the the sig modulus 2? What is sig modulus 2? Sig modulus 2. What is the remainder when sig is divided by 2? So we got 3, and the remainder is 0, right? So we got this one, 0 comma 2. Okay, because we have A equal to 0, so it is the basic step. So because we got A equal to 0, so the GCD is equal to B. Okay, we have B2. Okay, so the GCD of 2 comma 6 is 2. Okay, let's have a look on another example. Let's say 3 and 9. Let's see. Okay, right. So is in the same way, because A is not 0, right? So we'll have B modulus A. So we got 9 modulus 3 comma A, just 3, right? Okay, so let's have a look again. What is 9 modulus 3? What is the remainder when 9 is divided by 3? So we got 3, right? And the remainder is 0. So we have here 0 comma 3. And because A is 0, so when A is 0, so the GCD is a B. So we got 3 here. Okay. Okay. Now, by using the same definition, so we can put it in algorithm. So in programming, function will be a method, or in different definition, a method can be a procedure. Yeah? So method is basically the same like method, and method or procedure in programming is uh, equivalent with function in math. So if you are not familiar yet with programming, no worries, no problem. You can consider procedure or method or algorithm as a function. Okay, as a function. Function, you know, you must have been familiar with function, right? Function we have, for example, fx. For example, I think you have been familiar with fx, right? Fx like this, right? Let's say you have f, so it must be small, right? You have fx like this. This is the function we have been familiar with. So we have f is the name of the function, and x is the variable or in programming we call it as argument. Okay, argument. So for example, we have the name here is GCD. So basically it's the same like function name. Function name. Usually in your SMI you use just f, right? But basically it's just a variable, so you can name it anything. Yeah, for example, f, I change it to GCD. Okay, and the GCD we have two parameter here. We have a comma b. So basically in mathematics it's the same like you have fx comma y like this in mathematics. So a function with two variable fx comma y. But it's in math, right? So in uh, even though in programming you can change it with anything, right? Is it okay, right? If I change x and y with a and b, so it doesn't matter. So basically it's the same like f with the parameter a comma b. Okay, or f I can change it into any name, right? I can use key or h, or just using GCD like this, GCD of a comma b. Okay, and then we define this as like this. If a equal to 0, then GCD a comma b will be equal to b. Okay, else if a is not equal to 0, then we have a GCD of a comma b is equal to GCD of b modulus a comma a. This is basically what we have discussed before here. Okay. All right. Okay. So so generally we uh, define our recursive by calling the same function or the same procedure, but with smaller input or with smaller uh, uh, parameter. Okay, with smaller input or smaller parameter. Okay, for example, a GCD of, let's say, 3 and 9, right? 3 and 9. This basically it will be equal to, finally it will be equal to f0 comma 3. It's smaller, right? The previous one is 3 and 9, and from the definition of uh, our recursive, we got equal to 0 comma 3. Okay. All right, let's have a look on another example. Okay. Okay, let's have a look on another example. We have a power n. Okay, a power n. Okay. Uh, in mathematics, we can define like this. So fn, yeah, fn, in which fn equal to a power n. Okay. So in math, we can write it like this: fn equal to uh, of fn. All right, like this. It will be equal to uh, n a. Okay, like this. We have to f a comma n, like this. It's equal to uh, a power. Okay, a power n. Okay. So for example, if I have f2 comma 3, so it will be equal to 2 power 3. Okay, 2 power 3. It's mean 2 times 2 times 2. Okay, so we got it 8, right? Okay, all right. Okay, that's in maths we can define as a function like this. Okay, but in computer science we can change this function into a procedure or method. It's the same thing. Method or procedure is basically the same thing. So for example, I change f with power, and we have two parameter here or two input here. So we have a and n, in which a must be non-zero real number and n must be non-negative integer. Okay, so we can define like this: if n equal to 0, then power a comma n equal to 1. Okay, else otherwise, if n is not equal to 0, then power a comma n equal to a times power a comma n minus 1. Okay, so let's use this definition. For example, I have power. Uh, okay. Let's me text back here. Okay, let's say I have power. Okay, power a comma n, right? So let's say a is non-zero real number. So let's say 2, and n non-negative integer. Let's say 3. Okay, so we have what is power 2 comma 3. Okay, so let's have a look on the definition. If n equal to 0, is it n equal to 0? We got n equal to 3, right? So no. So we got equal to
a times power a comma n minus 1. So we got a is 2, right? So we get 2 times power a in bracket a, which is 2, comma n minus 1. Because n is 3, so n minus 1 is 2. All right. Okay. Okay, now we got this one. 2 times power 2 comma 2. Okay, now we got a is 2 and n is 2, right? Okay, so let's check, is n equal to 0? No, right? Because n is 2. Yeah. Okay, so we got this definition. Okay, so power 2 comma 2 is a, which is 2 times power a, which is 2, okay, comma n minus 1, n minus 1, n is 2 minus 1 is 1. Okay, all right. Then get this one, 2 times, sorry, 2 times 2 times power 2 comma 1. Now let's check this one. If n equal to 0, no, right? We got n equal to 1. So again, we use this definition. Okay, so we got power 2 comma 1 is equal to uh, power power sorry um, oh, okay, so we got this one power 2 comma 1. So basically it will be equal to a times for a comma n minus 1. So we got times a is 2, right? Okay, and then times power okay, a is 2, right? And then times n minus 1. So we got n is 1, 1 minus 1 is 0. So we got this one, 2 times 2, right? Now power 2 comma 0. Now put into the division is n equal to 0. We have n equal to 0, right? So it's correct. Because n equal to 0, then the value is equal to 1. So this one equal to 1. Okay, so we got this one. Yeah. 2 times 2, 4, right? 4 times 2 is 8. 8 times 1 is 8. So we got this one. Okay. Okay, now let's have a look on another example of factorial. Okay, factorial. So let's have a look on the example. Okay. Okay, factorial of n, right? N is positive integer, so like factorial of 3, let's say. So from this definition, we got n equal to 3, right? N is 3, okay? So check, if n equal to 0, then the value is 1. Because n is 3, it's not equal to 0, so we use the second definition, this one, okay? So also for simplicity, let's change factorial to f. Yeah, f, just to make it simpler. So we get this one. Let's see, it's equal to 3 times factorial f factorial n minus 1. So I got uh, n minus 1, 3 minus 1. So I got 2. Okay. And then we got 3 times f2. F2, n is 2 now, but n is not 0, so we use the second definition again. So we got n 2 times f factorial n minus 1, so we get f1. Okay, and then again, 3 times 2 times f1. Now n is 1, and we know that it's not equal to 0, so the same way we use the second definition. So we got 1 times f0. Okay, so we got 3 times, sorry, times 2 times 1 times f0. Okay, n is 0 now, right? So because n is equal to 0, so the value is 1. Okay, so we got 1. Okay, sorry, it must be 2, right? Okay, so we got this one. 2 times 3 times 2, 6, 6 times 1, 6, and then 6 times 1. So we got 6. So a factorial of 3 is 6. Okay. All right. So in the context of algorithm, we can define as two approach, two approach, two approach. Again, the same thing like in function in mathematics. In math, our function sequence of number we can define as explicit formula, which is in algorithm. We call it as iterative definition. Okay. This we call it iterative definition in programming. So iterative is start with the value of the function at one or more integer, the best case, and successfully apply the recursive definition to find the value of the function. So we have this two part. Yeah, the first one is the recursive definition, and the second one is the iterative definition. Okay, let's have a look on the example of Fibonacci. Okay, Fibonacci with one parameter or one argument or one input, which is n in this context. So we have n, and the definition is if n equal to 0, then the value is 0. Else, check whether n equal to 1. If 1, then the value is 1. Otherwise, the value of Fibonacci n is Fibonacci n minus 1 plus Fibonacci n minus 1. Okay, now let's have a look here. Okay, this one is the definition, a method or procedure or algorithm using recursive. Yeah, it's very simple, right? But we can use different way, which is we call it iterative method. It's quite long, right? It's very long, like this. If n equal to 0, then y equal to 0. Else, x equal to 0, y equal to 1, and then we make a iteration. Yeah, we make iteration. For I equal to 1 to n minus 1, I'll repeat. Okay, this one and this one are basically Both of them are correct. Both of them are correct. Okay, but we can have a look here. uh, by using recursive method, we can make our code, our coding much uh, simpler, much simpler. So let's have a look here. For example, by using recursive method, we just need 4 lines of code. Okay, we just need 4 lines of code. But if we didn't use uh, recursive method, you can have look here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We use 13 code, lines of code. So you can have a look here. Both of them are correct, but in terms of efficiency of line of code, we can have a look here. Uh, Recursive method is much more simpler, much more efficient. So if you copy your code by using recursive method, it's more smaller file. The size of your file is much more smaller. So for example, if you got uh, Android file, so your Android file is much more smaller, yeah, compared to uh, your program that it's written in iterative method. Okay, so both of them are correct. They can have the same functionalities or the same function, but by using recursive method, we can find that it can make the size of file is much more smaller. Okay, that's the benefit of using recursive definition. Okay, so we have test this one, right? That this one is correct. Okay, also let's check this one again. So let's say I have this one. So for the simplicity, I just use F. F stand for Fibonacci. Okay, so let's say F uh, 3. Let's say F3 like this. F3 like this. So we can put here n is equal to 0, no, right? And then n equal to 1, no, because n is 3 here. So it's it's the third definition, right? So we got f3 equal to f n minus 1, 3 minus 1 is 2, and then plus f 3 minus 2. So we got 1. Okay, all right. So we got f2 here, right? Okay, and then plus f1. Okay, now let's find f1 first. F1 first. Okay, or just I put like this first. Okay, again. Okay, and then because f2, let's find f2. N equal to 0 now, right? N equal to 1 now. So we put on the third definition. So we got f2 as f1, right? Because n minus 1, 2 minus 1 is 1 plus f n minus 2. So we got 2 minus 2 is 0. So we can find like this. Okay. Okay, so again, let's have a look on the definition. F1, n is 1. So if n equal to 1, then equal to 1. So we got this one is 1. Okay. F0 equal to 0. And F1 equal to 1. So we got this one is 2. Okay, and so on. All right. Okay. Now let's have a look using this one. Yeah, using this one. Basically, this one will be written the same thing. Okay, let's say here. Okay, let's insert the text box. Okay, the same way, just follow the instruction here. So F3, okay, F3, sorry, F3 equal to, okay, uh, this one is iterative, right? Okay, okay, if n y equal to fn, okay, so here we can find that if n equal to 0, then y equal to 0, okay, or y equal to f0. Is it n equal to 0? No, right? So we put else here. Else. Then we define x equal to 0. Yeah, x equal to 0. And then y equal to 1. Okay. We have initial value x equal to 0 and y equal to 1. Okay. Then we make iteration for I equal 1 to n minus 1. So we make iteration here from 1 until 2. Okay. From 1 until 2. Okay, right? Okay. So when I equal to 1, yeah, I equal to 1 here. Okay, I equal to 1 here. Okay, so we got z equal to x plus y. X plus y. X plus y. Okay, we got okay, x plus y. Oh my God. Okay, x plus y. X plus y. Okay, we know that z equal to x plus y. Okay, we know that x is 0 and y is 1. Okay, so we got z equal to 1, right? Okay, and then y equal to y. X equal to y. So now x equal to y. This is 1, right? Okay, and then y equal to z. The previous one, y is equal to z. Z is equal to 1 and y is equal to z. Okay, all right. Okay, like this. So y now is equal to 1. Okay, in the first iteration, I equal to 1 because we repeat 1 until 2, right? So now we come to the next iteration, which is 2. Okay, 2 here. Okay, here we got from here z equal to x plus y. From the previous iteration, we got x equal to 1 and y equal to 1 as well. So we got in the second iteration, we got z equal to, okay? And then in the second iteration, we got x equal to y. X equal to y. On the last iteration, we got y equal to 1, right? So we got x equal to 1. Okay, and then the last iteration is y equal to z. The last value of z is 2, so y is 2. Okay, and then y is because we repeat until 2 only, so we get out from this looping, this iteration. Okay, and then because we have done this one, so we finally reach this line. Y is Fn. So Fn or iterative frequency n is equal to y. We know that the last value of y is 2. So we got this one equal to 2. Okay, this is basically the same thing like before we got to. Okay, so uh, the value is the same, but you can have a look here. Uh, our recursive method can make the line of code much more smaller. Okay, so it is the end of our class today. Thank you very much. If you have any question, just make comment uh, on this video. Okay. Thank you very much. See you next week. Okay. Bye bye.